Today, we are going to discuss about bounded sets. Certain sets of real numbers, called intervals, occur frequently in calculus and corresponds geometrically to line segments. If A is less than B, then the open interval from A to B consists of all members between A and B and is denoted by a parenthesis of AB. The closed interval from A to B includes the endpoints and is denoted by an open and closed bracket of A, B. Using set builder notation, we can write open interval AB is a set of all x such that x is greater than A and x is less than B. Now, the closed interval AB is a set of all x such that x is greater than or equal to A and x is less than or equal to B. Note that parentheses in the interval notation and open circles on the graph, this one, in figure 6 indicate the endpoints are excluded. So the for this figure number 6, so we have an open dot or open circle. So meaning to say that value is excluded from the interval. Whereas square brackets, this one, and solid circles in figure 7 indicate that the endpoints are included. So intervals may also include one endpoint but not the other, or they may extend infinitely far in one direction or both. So the following table the possible types of interval for this. Okay, so these are the following table. So we have here the open interval of AB. So the description of this, we have a set description of x is a set of x such that x is greater than A and x is less than B. So in graph, so we are going to use the open dot, or sometimes we call it open circle. So that is now how to represent the graph for this notation. And then for the closed interval, AB is the set of x such that x is greater than or equal to A and x is less than or equal to B. So we are using here the closed dot, meaning to say the value of A and the value of B is included. And this one, we have a combination of the open bracket and the closed parenthesis. So it means to say it is the set of all x such that x is greater than or equal to A and x is less than b. So x is greater than or equal. That's why we write here the close dot. And for x is less than b, we use only the open dot. And the reverse of this, we have the open parenthesis a with a close b close. So it's a set of x such that x is greater than a and x is less than or equal to b. So in graphing, we are going to use an open dot for a and close dot for b. If you can see, there's a symbol of equal and less than or equal. As long as there's a symbol of equal, then you have to use the close dot. And this one, we have open parenthesis a up to infinity. So the set description for that is a set of x such that x is greater than a. So in graphing, the direction of the arrow now is going to the right because x is greater than a. And that a, there must be an open dot. And then for this, from negative infinity to b, we're using the open and close parentheses. So meaning to say, we have the set of x such that x is less than b. So the direction of the graph now is going to the left of b. With b, there is the open dot. And second to the last, we have negative infinity to b but close bracket, whose description of for that is a set of x such that x is less than or equal to b. So therefore, the arrow is going to the left of b, but we are going to use the close that. And for the last one, this is an open and close parenthesis of negative infinity to positive infinity. It means to say that the set description is the set of all real numbers. And this is symbol for the set of all real numbers. As you can see, all the lines in the graph is being shaded. Okay? We don't use neither an open dot or a closed circle if that is infinity. Okay, let's try this one. Express each interval in terms of inequalities and then graph the interval. Okay, for letter A, we have the open bracket -1 to 2 and then close parentheses. So how are we going to describe the set? So this one now, we can describe that one as the set of all x such that x is greater than or equal to -1 and x is less than 2. Okay, so to graph this one, this will be our graph. For example, this is now -1. This is just an approximate measurement. So if this is -1 and this is 2 and this must be 0. So it says there that x is greater than or equal to -1. Then we're going to use a close dot for this. Okay, and then an open dot for 2 because x is less than 2. So the graph now is that one. Okay, the one that we colored pink, and that is now the graph. Now for next number, we have the open bracket of 1.5 comma 4 close bracket. So in that case, we are going to write the set builder notation is a set of x such that x is greater than or equal to 1.5 and x is also less than or equal to 4 because we are using the less than or equal because it is a closed bracket. So in graph, so we're going to use the two ends using the closed circle or closed dot. So we have here, shall we say this is now 0 and this is 1.5 and this must be 4. Okay, so in graphing, so since x is greater than or equal to 1.5, then this must be a closed dot, and 4 is also a closed dot because of less than or equal, and then the shaded part for that is this one from 1.5 to 4. So meaning to say the 1.5 and 4 are included values. And for next number, we have open and close parentheses of -3 to infinity. So the set builder notation for that we can write as the set of x such that -3 is less than x. Or you can also write this way, or it could be written also a set of x such that x is greater than -3. So these two statements are just the same. As you can see here in the graph, it can be shown to the graph that, for example, if this is now -3 and this is to going to the infinity. So if we're going to graph that one, our graph will be going towards the right side of -3 because of this infinity. But we're using here an open dot. We use open dot for this, and then the graph is going there. Okay, so it's infinity. It means to say we can expand that one to infinity. So next we're going to discuss about the absolute value and distance. So the absolute value of a number A is denoted by this symbol, and it is the distance from A to 0 on the real number line. So look at this figure, and distance is always positive or 0. Take note, there's no such distance as negative. That's why we are going to take the absolute value. So we have the absolute value of A is greater than or equal to 0 for every number of A. Remembering that negative A is a positive when A is negative. We have the following definition. So if A is a real number, then the absolute value of A is A if A is greater than or equal to 0. The absolute value of A is equal to negative A if A is less than 0. So these are my illustration. For example here, if A is negative 3, okay, the absolute value of negative 3 is equal to 3. Okay, because if you're going to take the distance of that from 0 to negative 3 or negative 3 to 0, then the distance of that is just 3. Including this one, this is now the absolute value of 5. So the distance for that is just 5. Okay, so evaluating absolute values of numbers. For example, what's the answer for number 11? So the absolute value of 3. So the absolute value of 3 is just 3. Okay, the answer of this is 3. And then, what about the absolute value of negative 3? So the absolute value of negative 3, so in solution, we can write now negative of negative 3 is equal to 3 because we are using this definition. A is equal to the negative of A if A is less than 0. So that's why the negative of the value of A, which is now negative 3, therefore negative of negative 3 is equal to 3. So the absolute value of 0 is always 0. And the next example is we have the absolute value of 3 minus pi. So in that example, we can use now the definition, this one. So therefore, we could write now that the negative of 3 minus pi is equal to, using distributive property, this can be the negative times 3 is negative 3. I write first negative 3, and negative times negative pi is positive pi. Or you could be rearranging that one starting with the positive value. So therefore, we have pi minus 3. The answer now is pi minus 3 since 3 is less than pi. It means to say that 3 minus pi is less than 0. So we have the properties of absolute value. So number one, the absolute value of A is greater than or equal to 0. So the absolute value of a number is always positive or 0. So in example, the absolute value of negative 3 is equal to 3 because 3 is greater than or equal to 0. So number two, the absolute value of A is equal to the absolute value of negative A. That property, a number and its negative have the same absolute value. So if you're going to take the absolute value of 5, the answer is just 5. And the absolute value of negative 5 is also 5. That's why this property number 2 are equal. Then the absolute value of AB is equal to the absolute value of A times the absolute value of B. Okay, the absolute value of a product is the product of the absolute value. So to illustrate, using this example, the absolute value of negative 2 times 5 can be written as the absolute value of negative 2 times the value of 5. If we're going to answer this one, so negative 2 times 5 is negative 10. So the absolute value of negative 10 is 10. This one, the absolute value of negative 2 is 2 times the absolute value of 5 is 5. So multiplying 2 times 5, that is also equals to 10. And number 4, we have the absolute value of a quotient is the quotient of the absolute values. So this is what I'm trying to say. The absolute value of A over B is just equal to the absolute value of A over the absolute value of B. So in example, we have the absolute value of 12 over negative 3 is just equal if you're going to write the absolute value of 12 over the absolute value of negative 3. To simplify that one, we can have an answer of 4. And the last property, we have the absolute value of A plus B less than or equal to the absolute value of A plus the absolute value of B. So this kind of property, that's what we call as triangle inequality. So let's apply that properties in the next example. But we still have distance between points on the real line. If A and B are real numbers, then the distance between the points A and B on the real line is D stands for distance, and we have the distance of A and B. So the inequation that is now equal to the absolute value of B minus A. So let's take a look on this example. We have find the distance between the two numbers. I have negative 8 and 2. So using the formula, we have d of negative 8 and 2. So the answer will be the absolute value of b minus a, where b here is negative 8 and a is 2. So therefore, we have negative 8 minus 2. So the answer there will be the absolute value of negative 10, and taking the absolute value of negative 10 is just 10. Or you can do like this. We have the distance between negative 8 and 2 is just the same as if we are going to take the using commutative property, or let us start writing first. A is 2 minus negative 8. Okay, so they are just the same. I'm using the applying the commutative property from this position of negative 8 and negative 2, and the other solution will be starting 2 minus negative 8. Okay, so we have 2, negative of negative is positive 8, therefore a total of the absolute value of 10, and the absolute value of 10 is just 10, so they are just the same. So for number 16, so if we have the distance of, we have negative 3 to 5. So we have the distance of negative 3 minus 5. So negative 3 and negative 5 is negative 8, and the absolute value of negative 8 is 8. Or you can do the other way around. It could be 5 minus negative 3, still positive 8. So positive 8, the absolute value of positive 8 is just 8.